Hi, my name is Carly Lossie, and this is my presentation on Lab 4, which is about oscillations. In this lab, we have a mass oscillating vertically on a spring system. While this is oscillating on the spring system, the mass swings in an arc. Our goal is to construct a program that is able to model the motion of the spring mass system and compare it with the model with the observed system. There are a few important equations in this lab. The first is the kinetic and potential energy equation, which equals 1/2 the mass times the velocity squared. There also is the energy principle, which is featured on the slide. A few of our goals in this lab is to be able to predict the future using our initial conditions and relate it to Newton's second law and the energy principle. A few observations we would like to make is when it is in motion, the path of the mass is an ellipse-like shape. We will be assuming that no energy escapes, there is no air resistant, and the spring is massless. Moving forward, we will make some connections with our fundamental principles. This slide shows the work we did to calculate the spring constant Ks. Here it shows our process that we used to get to this variable, and then our actual value of the spring constant is Ks equals 6.83 newtons per meter. This slide shows how we calculated LO. It shows our process and how we got there, and our value, which is LO equals 0.123 meters. This slide shows the plot of the change in energy over time. The red line shows the change in potential energy due to gravity, the blue line shows the change in kinetic energy, the orange line shows the change in total energy, and the green line shows the change in potential energy due to the spring. As you can see, the potential energy due to gravity increases, so the potential energy due to the spring decreases. This is logical because when the string is pulled the most, it'll stretch more, resulting in the mass to be lower to the ground, which means there will be less of a gravitational pull on it. The kinetic energy oscillates, changing the potential energy due to the spring so that the gravity stays the same and the total change in energy stays at zero for the entire duration of the experiment. This slide shows the energy versus time graph. Everything that was said in the previous slide also applies to this graph, including the key. This is because the mass oscillated consistently, which means that the change in energy over time will be the same as the energy from time graph. In this slide, we will compare the predicted motion to the observed motion of the experiment. The predicted and observed motions are actually very similar. As you can see in the graphs, the x and y lines in the two observed graphs very closely resemble the green and red lines that are predicted in the graph, respectively. The only difference that can be found can be blamed on human error. Now we will discuss the possible errors that could have been made during our experiment and reflect on how we could improve our performance in the future. For problems, there could have possibly been an error in the code. Also, there's a chance that the push was included in our tracker video, which could have skewed the data. For improvements we could implement in the future, we could improve our prediction by beginning to analyze longer after the initial push. This way, there will be less of an impact from the push that would be acting on the mass, and the entire system be more similar and uniform. We could also consider the mass of the spring, which would make our prediction much more accurate. This slide will answer the first "what does it mean" question of the lab. The first question is related to the energy principle. The energy principle is satisfied in this reaction due to the fact that there is zero work being done on the system because of its surrounding. The total change in energy is in fact equal to zero. The plots that we see in the energy graph satisfies the energy principle because, as seen in the graph, one form of energy increases and the other form of energy does the opposite and decreases. This slide will discuss the second "what does it mean" question of the lab. This question is concerned about the periods of oscillation. The oscillation period is how long it takes the graph to return to a chosen starting value, such as 0. Starting at the origin and the graphs to the side, each oscillation period in the y-graph resembles a u, while the oscillation period in the x-data graph resembles a lowercase n. The period of the y-position data is about 1.42 seconds, and the period of the x-position data is about 1.52 seconds. This is because there is both spring and pendulum forces acting on the mass in the x direction. In conclusion, this lab shows us how the energy principle affects us in our everyday lives. As for the results, the motion model in the graph roughly fits the actual observed motion, and the modeled motion overpredicts the actual minimum and maximum values of the distance that was traveled by the mass. Have a great day.